So my name is Gernot Oretzky and I'm sitting here in Austria, and I want to talk now about our recent report that we wrote for the IEA Task 13, so which deals with performance and reliability of photovoltaic systems, and in subtask 3, which is called Assessment of Photovoltaic Module Failures in the Field, we made a really nice report which, let's say, summarizes the state of the art and the knowledge about failures. And my part was especially to talk about, let's say, the root cause of failure, so especially material interactions in PV module that are causing degradation mechanisms. So as a motivation, I pointed out some questions that maybe, let's say, a guideline for the next 20 minutes during my presentation. So what I want to answer a little bit is, why are material interactions and material incompatibilities important for PV module reliability? I want to answer a little bit the question if material interactions or degradation modes can be avoided. I want to show how the balance of materials influence the various degradation modes, and also, let's say, tackle a little bit the question if it's really possible to model PV module degradation modes. So, as you all know, PV modules are a very, let's say, complicated device. They are a multi-material composite containing glass, polymers, semiconductors, and various metals. So the core are the solar cells, which are encapsulated by so-called transparent encapsulant films. On the front we have the glass usually, and on the back we have a back sheet. So that is usually a multi-layer polymeric film. So what does happen when PV module, let's say, shows degradation? This is just a schematic graphic on a PV module, as I said, in front of the glass, the back sheet, and then we have the solar cell with the encapsulants. And this is just a graphic to show you actually the material streams and energy streams within a PV module during service life. So from the outside, we have UV light coming to the PV module that should be absorbed then, in the best case, by a solar cell. We generate electricity, so we have an electric current flow. But that's not all. We have a lot of other small molecules and ions that actually are, let's say, can be transported through a PV module. So from outside world, we have oxygen, water vapor, atmospheric gases and pollutants diffusing via the backsheet into a PV module. We have, within the polymers, we have additives, we have degradation products, we have maybe solvents that can migrate in all directions, and from the glass we have metal ions that can migrate into the encapsulation material. And actually, a lot of PV module degradation effects are just interactions between all these material flows and all these small or medium-sized molecules. And so, let's say, very common PV module degradation modes like yellowing, corrosion, PID, or snail trails are actually caused by these degradation effects. So what do all of them have in common? So all these processes are mainly influenced or driven by permeation processes of oxygen, water vapor, and corrosive degradation products. I will tell a little bit more about that in later pages. And that actually the polymeric materials play a major role in PV module degradation. So actually, that especially the encapsulation material is the main driving factor for most of these degradation modes. So how that? So what is the state of the art? In most of the commercially available modules on the market, so that's more than, or crystalline silicon modules on the market, ethylene vinyl acetate, in short EVA, is used. So this EVA has a very low melting temperature, so it is cross-linked during module lamination in order to get the desirable thermomechanical properties. And this material is in use since the 80s. So what is the pro of this material? What are the advantages? So it's highly flexible, it has a very high transparency, it's usually a low-cost material. It has a very good processability. You can make it very resistant to weathering, and most important, we have more than 30 years of experience and also field experience with this material. But there are still some drawbacks. As I said, the biggest drawback is this chemical cross-linking process, which is induced via peroxides that have to be added to the material itself. Then the lamination process takes quite long. So for, let's say, fast Q materials, it takes 10 to 15 minutes to produce one module. You need high amount of stabilizer to get this good weathering resistance, and that is not very cheap. So it makes the material a little bit expensive or more expensive due to that. And the biggest drawback actually, and that's what I already mentioned, it forms during degradation acetic acid. And what does it mean? So this is just a schematic reaction mechanism of how this acetic acid is generated. And this acetic acid actually quite influences the reliability of PV modules. So it accelerates the oxidation of EVA. So it starts some sort of an autocatalytic effect. So what can you see then? It produces more and more of this acetic acid, and sooner or later also we see yellowing and browning of EVA. Acetic acid is highly corrosive. So usually we observe corrosion of PV ribbons and also cell metallization. And it also enhances PID effect because it increases the ion mobility. So, as I said, EVA is used as the main material. But be aware that EVA is not a pure material. So it's not just the EVA molecules and that's it. Usually to polymers, you have to add additives and stabilizers in order to get the needed performance for each kind of application. And in our case, in order to get the 25 years of lifetime, we need to add UV absorbers, we need to add antioxidants to the material, you need to add hindered amine light stabilizers to the material, and because we need the cross-linking, we need to add curing agents that are usually various kinds of peroxides. So already the EVA film itself is not a single pure material, but it's a compound of polymers and various additives. And to our, let's say, what is very unfortunate, these additives can interfere with degradation mechanisms or actually can also cause or take part in degradation reactions. So I think the best example is browning of EVA. So this is just a schematic representation of how yellowing of EVA or browning of EVA actually is caused. So we have the pure EVA resins. Then we need, as I said, to put in all the additives and the cross-linking agents, so the peroxides. Then we cross-link the EVA during PV module lamination. Then we put the modules out on the roof, and we have UV exposure. So what are the absorbers doing then? So the UV absorber protects these chromophores that were built during lamination. So the material is not degrading. And then we must define or differentiate two causes. So on the one hand, when oxygen can diffuse through the material, so we have a backsheet that is open to oxygen diffusion, then the hindered amine light stabilizer kicks in, protects the UV absorber, and also it can be regenerated. And when we have yellow, it's slowed or it's, let's say, inversed via the photobleaching effect. But what is important now, when we don't have this oxygen presence, sooner or later the light stabilizer and also the UV absorber, they are photodepleted, and so more and more of these chromophoric degradation products can be built, and then we have an increasing yellowing rate with time. So this brings me to the next point, so that not only the encapsulant is responsible for PV module degradation modes, but also the backsheet has to play or has a very important role, and that's the role about, let's say, you can imagine it like a bouncer in a discotheque. So the backsheet decides what goes in and what goes out, And here are just some permeation rates for various backsheets are depicted for permeation rate of water vapor, of oxygen, and acetic acid. And we see, for example, for various kinds of backsheets, they're more or less in the same range for the water vapor transmission rate, except where we see here this PPE material, which has an additional aluminum foil. That means no vapors can permeate through this backsheet. This is then also the same for the oxygen transfer rates, where we see most of the standard backsheet types that have some sort of polyester layer. They show more or less the same oxidation transport rates. Oxygen transport rates. What was interesting is that the acetic acid permeation is somehow linked to oxygen permeation. So when we have a very high, or let's say high oxygen transport rates, then we will have high acetic acid transport rates, and vice versa. And so here this is an older material, so a pure polyamide material that showed this very interesting behavior where we had selective permeation properties. So that means quite a low water vapor transmission rate, but very high oxygen and acetic acid transmission rate. And actually, this is just by looking on the material streams, it's beneficial for a PV module because oxygen can get in, can prevent yellowing of EVA, but also acetic acid that is formed during service life can permeate out to some extent. So what does it mean? That actually just by design matching of backsheet and encapsulant, we can prevent, or let's say at least retard some degradation mode. So here is a nice example that was presented by 3M a few years ago, where they showed that actually by the choice of a backsheet with low water vapor transmission rate but high acetic acid permeation, and a modified encapsulant with a low water vapor transmission rate with increased volume resistivity and also enhanced additives, that they actually can avoid PID effect. Similar thing was shown, for example, by Yingli Solar 2 years ago at the Photovoltaic conference in, I think it's at the PVSEC. And here they used an ionomer film between glass and EVA to, let's say, to intercept the natrium, the sodium ions from permeation to the solar cell, and so causing these leak currents. And so actually, even with a very PID-prone EVA, they reduced, or let's say they completely avoided the PID effect. When we're looking at snail trails, also just by the right choice of EVA and backsheet types, this effect can be avoided, namely via its permeation properties, especially the water vapor permeation properties. So here is another case of what material interactions can do in a PV module. In this case, you see it's actually not the EVA that showed the yellowing, but it was just the backsheet that showed yellowing. And we found out, because we also looked above the cell, and above the cell there is no difference between the reflectance values, but above backsheet there is a big difference. And the very fun thing is, or the very interesting thing is, that we changed with EVA we didn't see this behavior, as you can see here in these values, but a certain combination of a thermoplastic polyolefin encapsulant and this backsheet showed this yellowing. So is this already, let's say, a failure by means of power loss? I would say no, but sometimes yellowing is also a precursor for let's say, following failure, and maybe sooner or later this backsheet will degrade too fast and then we will have other problems. So I cannot say yet. Corrosion. Here is again, we see the influence of acetic acid and on corrosion of materials. And the first picture, you see copper stripes that were laminated. in an EVA and in a so-called polyolefin elastomer. So that's a material that gets cross-linked like EVA but doesn't have this vinyl acetate group. And here we see just by leaving out the vinyl acetate, no acetic acid can be formed, and so we actually minimize the corrosive potential. But, and that's also the interesting thing, we did some studies with exactly the same material, and when we put this in a double class setup, actually found also for this polyolefin encapsulant corrosion effects. So that means not only acetic acid may cause corrosion, it's a very obvious source of corrosion, but also when you don't have this acidic or this acetic acid present, actually by other mechanisms, especially copper can corrode. And in our case, we just saw it because we made a double class module where, let's say, there were no permeation inside or from in and out the module. So let's say more harsh conditions than in a glass backsheet module. Here is also some nice interaction which was actually caused by soldering itself. So this is a low temperature, so a very new PV ribbon based on a thin bismuth solder, and we tried we wanted to check, let's say, that how this material performs. We made laminates, and the fun or the interesting thing was that just where we soldered these ribbons to an interconnector, we saw the formation of this thin hydroxyl peak, and we didn't see it just by laminating the ribbon. So we assume that actually the flux is causing this chemical reaction, and we are currently now looking more into detail if this sooner or later has, let's say, shows problems at the electrical performance. But I put this in just as a nice example of, let's say, how certain processing steps and also processing aids like flux can influence reliability or can cause, let's say, changes in material. So, and the last example is what happens when you do not cross-link your PV module enough. So when you have temperatures, too low lamination temperatures, or when you have too short times, what we found out what we showed in this study is actually when we put the modules then out on the roof or put them into accelerated aging tests, the module will cross-link due to these conditions. But after some time, we observed corrosion on the ribbons. So you see this in the yellow circles, this discoloration. And after, let's say, a certain amount, so several thousand hours of temp heat test, also the power output decreased just because of this corrosion. And we assume that actually the remaining peroxide that was not used during lamination caused, under service life condition, under UV irradiation, let's say, side effects that led to this corrosion of the ribbon. So, to summarize my last two slides, so what are the roles of polymers in PV module reliability and PV module degradation modes? So for the backsheet, the main role is electrical isolation and act as a barrier against atmospheric gases, and also to serve as a weathering protection of the inner layer. So what is the most critical failure mechanism of this backsheet is actually when it delaminates or when it cracks, and then it leads to a faster ingress of moisture and oxygen into the module. This can enhance physical and chemical material degradation processes, starting with embrittlement, microcracks, discoloration, corrosion, and so on, and also to further delamination within the PV module. And then sooner or later, usually in the field, we observe a decrease in electric power output, but also it causes safety issues because it's not safe anymore, for example, to touch the back of the PV module because we don't have the isolating effect anymore. So please keep in mind that the reliability of a PV module is strongly affected by the long-term stability of your backsheet, and also that your backsheet, let's say, you should choose your backsheet always in in combination with your encapsulation material. Because the right combination can decide about a good module with long reliability or a bad module. And just some final words, so keep in mind EVA is not EVA. So each encapsulation film you can buy on the market is a compound of raw polymer and various additives. That the encapsulation material plays an important role in the module reliability because most prominent failure mechanisms are linked to the encapsulation material. And that actually long-term stability is determined by the bill of materials and material interactions. So by, let's say, a good design of your module and a right choice of your components, actually you can produce better modules. Please don't talk about cost. That's the other side. And from a scientific point of view, you have to test each new material combination very thoroughly again before you bring, let's say, your PV module in the field. And in general, a better understanding of this material degradation processes and interaction is a precondition, to my opinion, for a very successful development of new components, but also new PV modules and PV module designs. And with this, I'm at the end of my presentation, and thank you for the attention, and I'm looking forward to some questions after the presentation of Ulrike.
Welcome to the second part of this webinar. Many thanks to Leonardi Energy and Fernando for hosting and moderating this webinar. My name is Ulrike Jahn from TUV Rheinland, and I would like to acknowledge my co-authors Marc Könkes and Arno Moyer from ISFH in Germany and Karl Berger from IEP in Austria. As a motivation to the next 20 minutes, I would like to share this slide with you. We have to deal and consider different risks during the phase of the planning to the operation, installation, and then end of lifetime. So it starts with environmental risk, which are often due to the location of the PV plant, typical technical risks such as performance and yield losses, degradation issues as we have seen on component side in the previous talk, as well as maintenance and repair issues. We also have to tackle safety issues such as electric arcing, fire, or theft and vandalism, and also logistical and political risks. Just as a figure, a very rough calculation, thinking about a 100 megawatt power PV plant, and assuming that there is 1% of power deviation, this will lead then in a result to €2 million revenue losses. And in order to avoid this financial loss, we have started with our work within IEA PV PES Task 13, first of all, to review different failures of PV modules and components. We have been looking for the background information, how the most important and relevant failures have to be considered. We have classified module failures from a systematic point of view, and we have described and also outlined the different methods how to detect failures in the lab and in the field. And this first work, and you can see the report on the right-hand side, deals with categorizing module failures and how to assess them. So with this background in our current phase, we have been doing two things. One was to really learn to understand how is the degradation process on one hand side, and on the other hand side to assess the failures in the field. And in the next 15 minutes, I like to give you some results of our surveys and investigations. And as mentioned before, cell cracks and snail tracks are relevant in the field, PID, but also delamination over the cell, defect frame due to snow load, for example, and I will also point out defect bypass diodes or moisture ingress, which can be seen from the front of the module. And with this, I would like to start with our first investigation using visual inspection methods worldwide. So we have collected data from more than 1,200 fielded PV modules in different countries. As you can see from the map, it is mainly centered in Europe, but we do have some data from Australia and the US as well. With respect to the climatic zones, most of them are in moderate climate, most of them are in cold and snow climate, then followed by moderate climate. For the module technologies, the silicon wafer-based modules on one hand side, but also to a very high degree cadmium telluride and CIGS modules, as well as amorphous modules. And as you can see, this is not representative of the modules which are installed in the field at the moment, but these are the data we were able to collect with respect to the failure issues. And this is already one of the first results with respect to the climate zone. So on the y-axis, you see the relative failure in percent. And we have looked for two main differences of different climate zones, the moderate climate and the cold and snow climate. And on the left-hand side, you see the most harmful failures with respect to the occurrence is moisture ingress and snare tracks in moderate climate. And for the cold climate, we have the defect frame as it could have been expected. If we try to look for the time when these failures happen with respect to the installation, so on the x-axis now you have the time period after the installation, which means in the first early time after installation 0 to 3 years, and on the right-hand side the time frame until 0 to 7 years after installation. You see again that there are, for silicon wave-based modules, for these two periods, that the snare tracks are typical dominant in the early years, between 0 and 3 years, while the defect frame and moisture issues come during the curve and the installation, the operation time. So this is just as a short summary. So even with very simple methods such as visual inspection, if you have a very clear failure catalog and classification, it is able to do statistics as we have started them, and we will follow up in the next years. So again, snare tracks and lamination over cells is very dominant for the first years, and moisture ingress to the modules in the years 0 to 7. And for both defect frame and moisture ingress, there's a very clear correlation to the operation time. And with this, I already will introduce you to a second database and attempt we have been tackling with this international expert group. So a data collection tool was designed, including PV failure data of PV modules and other components of a system from the field. So this tool was designed for international PV experts who would like to contribute to this data collection. And for the development, we wanted to realize that there's a maximum of anonymity for each of the plants. So as you can see here on the left-hand side, there is general data which needs to be provided, such as system site, climatic zone, etc. Then on the upper right-hand side, there are typical the types of the different components. And very important, you can specify up to 5 different failures with different failure modes, which you can attribute to each of the plants. And also this data collection tool is available on the IEA PVPS website, including a description how to use it. So our data we have collected so far from also different regions in the world is also centered in Europe with some 62%, but here we also have data from the US, from Canada, from Asia, and also from Australia. So a total of 148 data sets in 18 countries have been provided, and as you can see, the dry and hot climate is represented by 25%, and the temperate climate is represented by 46%. And the tropical, which is dry and humid, is represented by 10%. With respect to the module technologies, the highest percentage is by multi-silicon wafer, 62%, followed by monocrystalline PV modules, 28%, and about 8 to 9% of thin-film technologies. This is the first result of this data analysis of the failures with respect to the occurrence. That is the frequency of the failures as they were collected in the classified failure modes. And on the x-axis, you see the years after installation. So we have between year 1 and year 21 of a PV plant in these different regions. Here they are not classified according to the climate, and you will see very prominent cell cracks in the first 2 years, in the year 1 and 2, followed by the PID, PID with respect to shunting, that's what the S stands for, typical here starting in the year 3 and 4. Also defect bypass diodes, as you can see, and discoloring is occurring during all years, but there's an accumulation of discoloring of the potent, for example, in the year 18 to 19. So this is an overview of the occurrence, but we wanted to assess the failure of the modules and the system with respect to the power loss, and we have tried, or we have developed a method how to calculate the degradation rate of PV modules. And as you can see from this image on the right-hand side, the red covered modules, these are the failure affected modules. And first of all, the calculation, as you can see on the left-hand side, is for these affected modules. So there is a degradation rate. We have an overall power of the whole system of PI, that is the nominal power in kilowatt peak. And then we have the affected system part of the failure with index X, and it is the power loss which occurs and which was measured, divided by the time difference between the date of the inspection and the time or the date of when the first data collection has started. So that is a degradation rate, and with this calculation I can share these results with you. So it is the distribution of the degradation rate as defined before in the y-axis, and you see the different failures on the x-axis. So first of all, you can see that there are, for all failure modes, they have very high degradation rate variations. That is what these bars mean. You will find some numbers on top of the lines. These are actually the absolute number of the failure modes which have been collected. And it is also possible to calculate a mean value for each of these degradation rates. And in figures, if we now look for the PID with respect to shunting, we have a mean of 12% per year, while for PID corrosion it's 13% per year, and by bypass diode with 15% per year. And they are marked in the axis, and you can see that the variation is quite high. looking at the discoloring of the potent. That also occurs, but the degradation rate is rather low and stays well below 1% per year. If we go one step further, we also like to calculate not only the degradation rate of the affected part, but of the overall investigated part of the whole system. And that means that this degradation rate, delta Ix, is then defined as the degradation rate of the affected plant, and you multiply times the ratio of the affected divided by the investigated part. And with this method, having the data collected, we cannot actually say whether this is the degradation rate is a constant value, because we just have 2 points to calculate them. But on the other hand, if we do also then have the mean values and do a weighting of the mean values, this method allows to compare the different power losses for different system ages as well. And having this for the investigated part, and you can see it on the picture again, so there is one smaller part of your system which has the failure issue, and you are doing your measurements of the invested, that is a full green shaded part of the system. If you take care that the amount you investigate is large enough to be representative for your entire system, you can then try to calculate the degradation rate, the mean values of your degradation rates. And from the figures we have seen before, you can learn that most degradation rates are now reduced if we calculate them on the system level, because not all modules have been affected. That is very clear. So again, PID with respect to shunting, the result is a mean value is 8%, as you can see from the diagram, but with a high variation. PID corrosion, 12% per year, also with a variation, and the defect bypass diode with 10% per year. And these are all values which are relevant on system level. So typical cell cracks, the impact on the power loss is typical 2% per year, and again, discoloring is lower than 1%. Now, if we are trying to put this data into our different climatic zones, then it is interesting to see that the cell crack degradation rate with 8% is even highest in the moderate or continental climate, while PID, 16%, that is true also for temperate and moderate climate, but still very high variations, as you can see. And again, in tropical climate, we have the highest discolorating degradation rate, but with a value of lower than 1% per year. And with this, I already summarized these results from the second method, where we have collected degradation rates with respect to the power loss and have calculated different degradation rates. So cell cracks dominate in the early failures during year 1 and 2, and the degradation rate caused by snail tracks is highest in continental and snow climate. PID usually dominates in the year 3 and 4 in the failure statistics in moderate climate, but there's a great variation of all degradation rates, particularly for bypass failures, and also and they also cause a dramatic power loss. And if you have data to share and like to contribute to this work, you can find not only the results in this report in Chapter 3, but also on the website the data collection tool, and we will be happy to receive your input. So in general, to finalize both talks, this global network where we are working on quality and reliability of PV modules and systems. We are collecting and analyzing data in order to assess technical and financial performance. We have seen worldwide PV installations which do not fulfill quality and safety standards, and depending on location and level of quality and training, sometimes there is very little knowledge on the extent of installations and failure mechanisms and also failure statistics. And this is for us the reason to further improve methods in the field, also the modeling of the PV module power degradation with respect to more qualified assessments of PV systems, and this is in order to lower the risk for PV investments. And with these final words, I would like to thank you for your attention, and we are happy to receive your questions.